Hello and welcome to another one of D's ADD videos. We're going to look at the volume of solid revolution. Again, the basic concept, it's the integral of the outer area, cross-sectional area, minus the inner cross-sectional area. If our cross-sectional area is a circle, as in one function rotation about the x or y axis or some line, then it's the disk method. But if we have two functions, like in the example shown here, what ends up happening is we have this whole gap in the middle that results in a hole here, creating a washer-like structure. Alright, so the concept's still the same. We're going to do the outer minus inner radius. Alright, so the only difference is the inner radius now is no longer going to be 0, it's going to be some function. And then you integrate across the x-axis would be dx, across the y-axis would be dy, and that's the washer method. They're basically the same thing, but just make sure that you know which region you're integrating with respect to, and we're going to use this example to illustrate it. So I believe what I had was the square root of x and x equals 1. Or y equals x, sorry, not x equals 1. Early in the morning recording, still not fully awake. So the region of interest is going to be this one here, and when I rotate it about the x-axis, what ends up happening is I get something like this. Alright, I don't think that line's too straight. Let's make that straighter. Alright, so the blue shaded regions are when we are flat on the XY plane, we get these blue regions, but if I were to rotate it about the axis, I'd get a vase-like bowl. Alright, if I take one cross-sectional area there, it looks like a circle, but there's a hole on the inside created by this function y equals x. So that's enough of that. Let's actually apply the formula now. It's going to be the integral of the outer minus the inner areas. So if we do, the outer function was root x, so it would be pi root x squared minus pi x is the inner radius squared, and that would go from 0 to whatever that point is, and the way we would find that is we'd set them equal to each other, and if we square both sides we get that, bringing that over to the other side through subtraction, then factoring out the x that's common, we get that x is equal to 0 and x is equal to 1 are the two intersectional points. So now it's just a matter of simplifying and integrating. So we got pi x minus pi x squared over 2. Then that's evaluated between 0 and 1. And when I do that, I'm going to get a pi minus a pi halves, and then minus 0. So pi minus pi halves is just pi halves, and that will be your area of that region. Or, sorry, volume of that region. Alright? I hope that has clarified any confusion about the x-axis ones. Let's try the same region, now rotated about the y-axis. Would give me something like this, and then now what forms the outer radius? Well, now it looks like the y equals x line is forming the outer radius, and the root x is the inner radius, right? So this was about the x-axis. This one's about the y-axis. So the difference here is you're going to have to solve for x on both equations. The y equals x equation is pretty straightforward, but y equals the square root of x. How do you solve for x there? Well, what's the opposite of square root? Squared. So you square both sides. And then you get y squared equals x. What was the outer radius? X. In this case, y. So it would be pi y squared. And the inner radius was pi y squared squared. In that case, we would go from 0 to the intersection point was at x equals 1, so if I plug in a 1 for x in either equation, I get y equals 1. So now it's just a matter of simplifying. We can factor out the pi. We're left with y squared minus y to the fourth. That equals pi y cubed over 3 minus y to the fifth over 5. So we got pi times 1/3 minus 1/5. Common denominator 15. Give me 5 minus 3 over 15. Or 2 over 15 pi. And that would be the volume of that solid revolution. Okay, and those are two examples of basic washer methods, right? So again, concept is outer minus inner for the volume of that cross-sectional areas, and in this case, when we do that, we have different shapes for the x and the y-axis. The x-axis in red over here, and the y-axis in yellow. And you're still going to need to figure out their intersection points. You're going to need to figure out which one's the outer radius, the inner radius, and then integrate. And if you're doing the y-axis rotation and a revolution, we have to do an extra step of solving for x and plugging the functions in terms of y dy. And that's basically about it. So practice, practice, practice. And check out the example of rotation about a line. Thank you and have a nice day.